Hello. Okay. Good afternoon, everyone. I hope you hear me well. So let's start talking about content management and artificial intelligence-driven world. We are in Drupal Plus technology track, supported by Platform SH. Thanks, Platform SH, for that. And as I said, we will be talking about content management and machine learning and how these things are related. All slides are published in GitHub, so you can view them in GitHub pages. There is a short link. You can view it here. It's bit.ly/Drupal Europe-ML. There are also speaker slides, so if you want to read them during the session, after the session, I will paste a short link in Twitter and also in the session description, so feel free. I hope that we will have Q&A section in the end, so if you have some questions, think about them. I'm also okay if you interrupt me, but in this case, it will take a little bit longer. So, a couple of words about me. My name is Valery. I work for a FOW agency. I'm okay if you call me Valery, Valery, or Valerie. Originally, it's Valery, but I don't mind, as I said. You can find me virtually anything as Valdebold on Skype, Twitter, Facebook, Drupal.org, and so on. So, as I said, I'm Drupal developer in a FOW agency in Sofia, Bulgaria. And I'm also a contribution mentoring lead. So, as many of you have heard and know, that on Friday we have dedicated day dedicated to contribution. Everyone is invited. We have a workshop for first-time sprinters. Then we have mentored contribution. So if you don't have any experience contributing, you're welcome. If you have experience contributing, you're welcome too. So everyone is welcome. Please not only attend sessions, but also on Friday we have the full day of contribution. That will be fun. So I wanted to start with okay, machine learning is not a high math, but unfortunately that's not true. That's quite opposite. There is a lot of high math involved in machine learning, and we will talk about it. I will try to explain it in a most plain English as possible, but still there is linear algebra involved, so I will have to use some formulas. Sorry for that. So what we will discuss? We will discuss what is machine learning, what classes of tasks we have in machine learning, a little bit about neural networks, then what are the methods of learning of hypotheses that we have in machine learning, gradient descent and stochastic gradient descent. And in the end, I'm going to talk about online learning because this is the most relevant thing for us as someone who builds and develops sites based on some content management system. Here, it's not important that much that we use Drupal because those concepts are universal, so they can be applied to any content management system. This short session was greatly inspired by the excellent online course. It is published on Coursera. The link will be in the end on the last slide. So this is the course on machine learning by Stanford University. So if you're interested, I heartily recommend to go to this course and start learning. It takes about 3 months, give or take, depending on your own rate. What we will not discuss today, because machine learning is a very wide topic and we will not be able to cover all of it. And there are a lot of excellent resources that cover different topics, so I'm not going to talk about usage of existing SDKs, APIs made by big companies like Google Cloud SDKs or Azure services or Facebook recognition APIs. I will not cover it. If you want to hear more about that, there is an excellent webinar made by Pantheon, and the link will be at the last slide. So they cover very real use cases of patch.com. For those of you who don't know, this is a local news, hyper-local news company, and they use Drupal, and also they have really very real use case for using Google Cloud SDKs with Drupal to to sensor content added by the end users. We also will not talk about tasks that have known solutions like auto tagging. There are models for that. Or face recognition. There are models for that. We can just in Drupal include these models and start using them. So instead, I'm going to focus on some unknown land, on topics that don't have ready solutions, and let's jump into it. I also will not talk about robots will take over the world and any magic or conspiracy behind the artificial intelligence and machine learning, because this is not relevant that much. So let's start with the beginning. What is machine learning? So earliest definition that I could find is that machine learning is a field of study that gives computers the ability to learn without being explicitly programmed. So this definition is kind of intuitive, but it doesn't help me to start with, or what steps should I perform in order to start learning my machines to improve how the sites that I build, to improve their performance. Now we have more formal definition, is that computer program is said to learn from experience E with respect to some class of tasks T, and performance measure P if its performance as measured by P improves with experience E. So this is much more sciencey. So we need to understand what are these E, T, and P when we are talking about content management. So let's imagine you start to build a site that has multiple pages. It can be informational site, or it can be site that actually sells something. So you have different business models for sites. You can get revenue for just showing pages to visitors if you run ads on your pages. If you run commerce site, then you actually sell items, and then you benefit from sold items. So let's say I have electronic shop. So in this electronic shop, I have multiple items, and I constantly keep adding new items and updating existing ones. So the answer that I ask myself constantly is, okay, we have tens or thousands or tens of thousands items. And of course, the space that I have on a web page is very limited. And of course, items that are placed on the home page, they will be perform better than pages that are hidden somewhere in the long hierarchy of my categories. So how do I decide which items to put on the home page? Or how do I decide what items to put on a featured blog, or a bestsellers blog, or most relevant blogs for the user that currently viewing my page? So I will try to apply machine learning for this specific task. So let's say we have experience, we have performance, and we have T. So let's start defining these variables. So experience is all the data that we get from our visitors. So it can be aggregated from the weblog, from Google Analytics, from a million other sources. It can be Elasticsearch, logging, or someone else, or something else. This is experience. Now, what is T? T is class of tasks that we're going to do. So I'm going to predict what will be performance, and I will talk about performance a little bit later, of pages placed A on the top menu, B on the bottom menu, C on the featured products block. So I have these three variables of performance that I'm going to measure. And I want to predict them for new products, and to learn how, if I have a no product that obviously I don't have any experience data about it, I still need to be able to predict how it would perform in these circumstances. So this is T. This is the task that I'm going to perform. So now what is P? P is actually accuracy of my predictions compared to actual observation. So what I'm going to do, I'm going to build some model, and then I will compare predictions of this model with actual users' data. So this is the process of machine learning. I have mentioned before digging into specific Umami website dilemma. I guess you know that I have showed a screenshot from Umami theme from Drupal 8.6. Let's talk about different classes of tasks of T that I mentioned in the definition when I was talking about what is machine learning. So machine learning class types can be divided into different groups. So one big group of tasks is called supervised learning. Supervised learning means that in experimental data that we have, we know the correct answer. For example, if we're talking about website performance, so we get data from the user, and we can measure performance. So we can know what is the click-through rate for the specific product when it is placed on the menu, because we know it. We know what is the average price of a purchase of new users coming from the United States, right? This is a known fact that we can measure. We get it from end user data. So first task class is called regression. Regression is when we're trying to predict some value or set of values that lay in continuous range. Example, let's say we have some experimental data for the price for the house prices in California. So we have this data, and we have a new house, and given its data, we will try to predict what will be the reasonable price for this house. So this is regression. In contrary, when the value that we predict and what we have in experimental data is binary, this task is called classification. Examples of these tasks. So if you're looking at the picture, you should tell if it's a male or female. Or once again, you look into the picture and trying to say whether this picture contains text or not. If you get an email, if this email is spam or not. So that means that all the algorithms that Google places into Gmail, they work on this classification task. You may wonder how it can be that we don't know the correct answer. Example of machine learning tasks where we don't know the correct answer is clustering. Does anyone here uses Google News or some other news aggregator? Okay. But if you search something in any search engine, the results are grouped by topics. And if you get a new experimental data, you cannot say in advance what is the topic. And the clustering tasks is actually analyzing different items from the experimental set and telling, okay, this group of items probably belong to one cluster. This is what news aggregators are doing. They are not pasting, they are not outputting links to the same article just copy-pasted by different news feeds. They're just outputting one link with maybe related, or you can be interested in other articles on the same topic. But still, it's the same cluster. And the thing here is that in experimental data, you don't have this label. You just have a plain list of all news items, so that machine needs to be able to group these items by logical groups. That's only one example of clustering task. Another task is that, okay, you want to print 2,000 t-shirts for a big conference, and you have data of, you have physiological data for attendees. You know the height and weight and gender for every attendee. We will put GDPR aside for the moment. But you have this data, let's say, and of course heights, and you don't have really groups there. But still, when you order t-shirts on the factory, you need to say, I want this number of L, this number of S, and this number of M. And also you need to say what will be exact size of L, M, and S. This is also an example of clustering task. So you get entire group of entire experimental set, and you try to divide it into some clusters, but you don't know what are these clusters. Second example of unsupervised learning, where we don't know the answer, is dimension reduction. For example, in image recognition, in text recognition, so if you have images of text, we need to recognize every letter. So this is definitely a classification problem. So when you look at the letter and then you say, this is 0, or this is O, this is A. So you have experimental set and you know a correct answer for each item in this experimental set. But you have a good camera and you tend to create your experimental set with high resolution. Okay, you can have dozens of megapixels in your camera, but it's not necessarily means that for recognition you need all these megapixels. Maybe you need only 70 by 70 pixels, and that will be enough for machine to be able to recognize what letter is it. And this task is called dimension recognition. So instead of working with huge data sets consisting of images, each of them is 2000 by 2000 pixels, you find the minimum size of an image where you're still able to recognize digit and do it precise enough. Third type of unsupervised learning tasks is anomaly detection. It's also very similar to classification task. Let's imagine that we're working with some airplane turbine, airplane engines factory, and we're trying to predict based on known engine parameters if it will be defective or not. Okay? So our task is to be as precise as possible. So to be as precise as possible and knowing that, well, there is a very high chance that the engine is good, the best option is to say that the engine is always good. And that way, our prediction rate will be high. But it will be useless for the manufacturer. So instead of telling always that engine is good, we'll try to analyze what are parameters combinations that are out of normals, let's put it that way, and only in these cases report that engine should be checked once again maybe, and there is a high chance that this engine is defective. So, for every class task, the learning flow is more or less the same. So we have some model. So let's say we have classification task. We need to look at some image and say what letter is in this image. So we need to come up with some function that will have, let's say we are working with 100 by 100 images. And that means that we will have a function of 10,000 parameters. And this function will return either 1 if we think that this is 1, or 0 if we think that this is not 1. So this is an example of a hypothesis function. Then, so this function has 10,000 input parameters, This is function of 10,000 features, it is called in machine learning, and then it can have as many parameters as we want. So initially, we set these parameters to some initial values, check with our training set, and see how precise are our predictions. Of course, if you put some random parameters initially, the result will be bad. And by playing with these parameters, you're trying to minimize the difference between your prediction and the end result, so you can predict really well. Okay, so if we return to our original task, is to understand performance of our commerce website. So let's say we have visitor demographics. What is country, what is user language, what time of day. If it's a logged-in user, then we have previous history. We have maybe current page data, what are categories of this item, of this product that we're selling. How fresh is this product, and if it appears on the top menu, if it appears on the bottom menu, we can have really many parameters that we store in our experimental data. So in machine learning, these parameters, this input data is called features. So we have input features that we have them in experimental data. And then we are trying to predict how long every user would spend on a page, what would be click-through rate, what is the probability of purchase, what will be average purchase amount, and so on and so on. So we have input data and we have output data. So traditionally in machine learning, input data, input variables are called features, and output variables are called labels. So in our example of commerce website, we have multiple features and multiple labels. But before we talk about multiple features and multiple labels, let's talk about simpler case, when we have only one feature. So since all of our labels can be in continuous range, so CTR can be any from 0 to 1. Purchase also can be anything in a range. Time on a page is also a float value. So this is a typical regression task. And the simplest and the most popular and most commonly used type of regression is linear regression. So let's talk first about linear regression with one feature and one label. So let's talk about task of predicting house price based on its square, on the square of the living space, okay? So on this figure you see experimental data. So on value X you have a square in square feet, and on Y-X you see value in thousands of dollars. So this experimental data of maybe California, I don't know, maybe something more cheap. Maybe California some years ago. So I will assume, so my guess is that best prediction can be made with just a linear linear function between price and square of the house. So that means that my prediction will be that I have some constant part of my prediction, and then another constant that will be multiplied by the square of the house. That's my prediction. So the actual meaning of these constants is as follows. So theta 0 is just an offset of this line from 0, from this point. Oh, you don't see it. So this is the meaning of theta 0. It's offset from this line and 0. And theta 1 is just a degree of slope. How steep is this line? Now, this is my hypothesis. How do I optimize it? How do I come out with good values of theta 0 and theta 1? So that, what is the learning in this case? Obviously, I have experimental data set consisting of, I don't know, I have bought a database of real estate sales from some broker, and I'm analyzing it. So, once again, my hypothesis is that price h, is some constant value, and then another constant value multiplied by the square of the house. So the intuition is that the cost that I'm going to minimize is that the difference between my predicted price and the actual price should be minimal, right? So how I will measure this price? So I come out with a price function. So I will define my price function as a sum of differences between my prediction and actual price squared, just to remove differences coming to plus and minus. So I always have positive cost for any observation, divided by the number of items in my experimental set. This is just by definition. So I have this cost function, and I'm going to minimize it. I minimize it. So this is a function. Function j is a cost function, and this is a function of two parameters, theta 0 and theta 1. So with playing with this theta 0 and theta 1, I must count to some point, to some combination of theta 0 that will output the minimal value of j, so that my aggregated mistake on household prices will be minimal. So the mostly used method for finding this is called gradient descent. So it works like this. So let's say this is the imaginary plot of some cost function, which has, yes, we have here theta 0 and theta 1, and this is a function of those two variables. So we start from some point. It's plotted in orange, somewhere in the middle, and see what is the direction of change of theta 0 and theta 1 that minimizes my current value. So I start from some random value. I measure what is my j function, and I look what is the direction where I should change theta 0 and theta 1 so that the total cost function goes down. So I'll make small step in this direction. I go again over the whole experimental set, and I find another direction. So if you have studied calculus, you probably have an idea that to know the direction where I should go with changing my theta 0 and theta 1 is called derivative. Since this is a function of two parameters but not one, we will be talking about partial derivatives. So for every j, so we have actually two thetas, theta 0 and theta 1. So we take theta 0, we take partial derivative of our cost function, and reduce our theta in the direction of derivative. There is one parameter called alpha. I will talk about it later. It's called learning rate. And this, for now, you should know that this is something small. And we perform this step until we go to some local minimum, meaning that no matter what changes we perform with theta 0 and theta 1, price function can only go up. So there is one danger with gradient descent method in general. If you look at this figure, you can see that if we go into that direction, then probably we are good, right? And we're going to the global minimum. But we could go into the wrong direction and end up in local minimum, where we have, do you understand what is local minimum and global minimum? So you can have very complicated shape of a cost function. So you can have some local minimum that lies higher than the global minimum. But the reason that linear gradient descent is so popular, there are several reasons, of course. One reason is that this is the simplest method. And the second reason, I will not prove it mathematically, but just believe me, linear gradient descent has only one minimum, so we should be safe. No matter where we start, we will always go to the global minimum because there is no non-local minimums. So I repeat this step until we go down to the lowest value of cost function. So we should be fine. Now, once again, this is just a bit of mathematics. So if you remember, our cost function is a sum of squares of differences between our predicted price and actual price. And we go over the whole experimental set, measure these differences, sum them up, and that's our cost function. This cost function has known partial derivative. So for theta 0 is just a constant value, which have just a sum of differences of our predicted price and the actual price. And for theta 1, which is multiplied by the square itself, it's a sum of differences between our prediction and the actual price multiplied by actual price. Just to give you an idea that what is the difference between regression and classification problem. So for regression, we just use linear function. It's just some constant value plus another constant value multiplied by x. For other tasks, for other class tasks, price function, cost function can be more complex. For example, if you're talking about a classification problem where we need to say whether the answer is yes or no, we obviously cannot come with some linear function that can return any value from -infinity to +infinity. So we need some function with values from 0 to 1. So this is an example of mostly used function for classification, and it's called sigmoid. So it's more complex, it's more computationally expensive, and let's focus on simpler problem of predicting website performance. Now, it can be that the dependency between real estate property and its price is not linear. For example, if you have bigger house, then probably it will be more expensive, and it will be more expensive than linear dependency. So what if the prices go much higher for bigger houses and don't change that much for smaller houses? So then we probably need to adjust our initial assumption. Luckily, we can stay with linear regression. We can keep the original formula linear, but we can say that, okay, we have our square of our real estate in meters or square feet, doesn't matter. And then we add another feature. We call it x2. And this new feature will be just a square of our square. Okay? We can add another feature, call it x3, and that will be square root of our price. So we can use our imagination and add as many features as we want, given only the square of our property. So our cost function still remains, our hypothesis still remains a linear function. We have some constant value plus some constant multiplied by x1 plus another constant multiplied by x2 and so on up to xn. Also, this will be correct if we're talking about our original task of predicting website performance, the CTR and purchase and other stuff. So we have a lot of features. We call them x1 up to xn. And this will be our hypothesis that the dependency between those input parameters and the CTR will be linear. And if we think that it will not be linear, then we will add non-linear parameters to the same equation. So we will keep the whole process still as linear regression. So if I look at this, if I look at the third equation, which is theta 0 plus theta 1 multiplied by x1 plus blah, 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 theta n multiplied by xn. So what, and once again, x1 to xn are my features. These are my input variables. We have a short form of writing the same in terms of linear algebra, in terms of multiplying matrices. So this is this form, which to me is a little bit more shorter and compact. It's the same as multiplying a row, a matrix that consists of one row, by matrix that consists of one, what's the name? Sorry. Column. So this is the same. The third row and the fourth row are the same. I just made one assumption that in my input variables, I always have variable called x0, and it always equals 1, so that I come up with exactly the same result. Now, I have mentioned that for original task, we need to make several predictions. So we need to predict CTR, we need to predict average time on page, and so on and so on. And that means that the output of our prediction function should be not one number, but two numbers, or three numbers, or several numbers. And that means that instead of multiplying a matrix that consists of one row, I have matrix that consists of several rows, depending on number of labels that I want to predict. Multiplied, once again, by a row from experimental set. So here's the trick. We have these values, theta starting from 1, 0 to ln. L is the number of labels, n is the number of features. I have x's, which are experimental data. So my task is to know what are values of this theta matrix that minimize the cost function. So this is the learning process for a linear regression task. This is essentially the same form of finding partial derivative for theta j. So let's say I have n thetas, and for every theta I get a sum of differences between my predicted value and actual value multiplied by experimental value. And this is the cost function. I'm sorry, I know this is a lot of mathematics, but please bear with me. So the process of going down with our cost function, again, we have some random values of thetas, And we need to come up with good values of theta that have the minimal value of cost function j. So the process is as follows. On every step, we take the current value of theta, we take partial derivative, which is just a mathematical formula. It's multiplication of two matrices. And we go over all experimental set, and we divide it by number of items in experimental set. So this is just, mathematically, it's very clear procedure. There are two fallbacks here, two pitfalls. First pitfall is that if you have a really big experimental data set, like it can be for website visitors, then working with matrices of big sizes that contain tens of thousands of elements and have multiple features and multiple labels can take a lot of time. And that's one of the reasons that we don't do it in plain PHP, and actually in no language. No one today implements this multiplication of matrices in any language. You can have a good library like TensorFlow for Python, or which is supported by Google, or other Python languages. Python is very popular for machine learning. So we don't reinvent the wheel, we just use external libraries. We have good libraries for PHP as well. The most known is PHP ML, and the link will be on the last slide. So this is one pitfall. Second pitfall is that if you have imagination rich enough, you can add so many features that you can optimize or overfit your experimental set. So if you have this, remember this original picture with house prices. You have a lot of points there. You can up with very sophisticated hypothesis function with a lot of features, so that the actual prediction will match exactly your observation. But if you take a new observation, it is a very high chance that your prediction will fail. So that's another pitfall, that you shouldn't overfit, you shouldn't minimize your prediction function too much. So this is my best, this is the point that I like most in machine learning, is that it actually penalizes itself for adding new features. That's a concept that we should start doing no matter what in web development. If you want to add a new feature, you should be penalized for that. So here's my first line with original step of changing theta. Now on the second line, I do the same, but in addition to just subtracting partial derivative, I also subtract a small part of value theta divided by the number of items. Why do I do that? I do that just to avoid this overfitting that I have mentioned earlier. So if some feature is not significant, it will be reducing itself all the time because of this value. Because we're taking the current value of theta and then we remove it, and then we decrease in its value with this another constant parameter which I call gamma. But actually, there is a third pitfall. So when you have many features and you start playing with different combinations of these features, of squares of features, you can really fast go crazy with number of features. For example, imagine that you have 5 original features. Then you have 25 combinations of multiplications of these original features, and you have even more if you take the third level, and so on and so on. So there are better methods of optimizing features that don't use linear regression functions, and the most known method of using the adjusting non-linear dependencies between features is neural networks. So how neural networks work in essence is that you have multiple features which are input features, and you use the same hypothesis function for this input layer, but you don't set in advance what are dependencies between features. So you don't say that I have a new feature, so you have 5 initial features, and you have 25 more features that are just combination, that are multiplication between x1 multiplied by x2, x1 multiplied by x3, and so on and so on. What you do instead, you let different layers of this neural network to decide what are the weights of connections between these different features. But this is, I will leave it outside of the scope of this talk. Now, yeah. So, how do we train our hypothesis function? So we always, if we have ready experimental set, it's a good practice to divide it into 3 parts. Say 60% or something like this we take for training set. Another 20, it's called validation set. One is training set, second is testing set, and third is cross-validation set. So how it works? We get our hypothesis function, we optimize it on the training set, and we check all the parameters on the training set. What does it mean? So if we have good imagination, as I told, we have overfitting, and that means that we predict well our original training set, but we fail to predict anything that lays behind our training set. So we should stop somewhere in the middle where the prediction for the training set is good enough and for the cross-validation set is also good. Now, I think it's time to return to our original problem of optimizing the performance of items that appear on our website. The difference between everything that I have just described and our real work is that we don't have a ready experimental set. But instead, we have a constantly arriving data about our users. So in order to understand how we can work in these conditions, let's talk about more advanced method of optimizing our parameters J, which is called stochastic gradient descent. And it's also related to the online data that we have in practice for all website performance that I have mentioned. So what is stochastic gradient descent? So when I was talking about regular gradient descent, it is also called batch gradient descent. In order to find the direction where I should go in my gradient descent, in what direction should I change my parameters theta, I actually need to go for, I need to go over all items in my experimental set and find what is the difference between my prediction and the actual value. So this is the full gradient descent or batch gradient descent. But if you have a big experimental data set or your data set is constantly arriving, so it's more of a streaming data set, you don't have this option. So you cannot just go over all data set all the time. So the gradient descent works in radically simpler way. So let's see what happens here. So the assumption here is that the change in the direction in which we should change our theta parameters is the difference between prediction and actual result, multiplied by actual result. So instead of going over the whole experimental set, I can take one data from this experimental data set and do the same. So in this case, m equals 1, so I don't have this sum. And the only thing that I have is the difference between my prediction and the actual value multiplied by the actual value. So this should be changed, so this is derivative. And if I return one more slide, so I should take original value of theta and decrease it by this difference. So this is how stochastic gradient works. I take the current value and I change it very, very little, depending on the last value. So this method converges slower than the standard gradient descent because, people are different and their preferences are changing. So there is a chance that you get some value and it actually changes theta in the wrong direction. But when you take the many values, many visitors' data, the result should be the same or closer to the same that you get with regular gradient descent. So this is actually how also online learning works. So you get the streaming data, you get the data about new users. And in addition to this much faster processing of new results, you have another benefit. You don't have to store the data about old users. You get the data about a fresh user, you process it, you change your theta parameters, and you throw processed data away. A bonus of this approach is that this process adjusts to changing user preferences. So if economy goes down and people tend to buy cheaper goods, then your parameters theta that are measured experimentally, they will adjust automatically. So this is how it works in theory. So it's a matter of defining the right features and starting collecting the data about theta. And then if you have a new product, you just apply this prediction function to a new product because you know the values of this new product. And you can compare the prediction of click-through rate, of page time on a page, average purchase with existing items in your top menu or featured block. And if new product is expected to perform better, then you just replace the worst performing item from the featured block. So everything is good. So remaining tasks, write everything this. There are a lot of tools to do that. No ready models, as far as I know, for Drupal. As I mentioned, there are ready models for Drupal that answer different machine learning tasks. And there is a good article describing the best models that you can find in 2018 that use machine learning and have ready or close to ready status for Drupal 8, so you can start using them right now. So I'm sorry if it was too much of mathematics, and if you have any questions, I will be ready to answer. Yeah. Questions?
Basically, you're not using some libraries. You did it with the clean language. I mean, with pure language.
No. So I'm not using, because this is not a ready solution. This is just an explanation, very short one, of how things work or should work, or what happens when machines are trying to optimize a parameter.
Yeah, but you don't create all this math by yourself?
No.
Okay, I got it.
Okay, then thank you everyone, and see you on Friday.